Welcome to qnawire.
Hi, so for this problem, we're going to have the following reaction of formation of a complex compound, and we're given the amount of mole that we're adding of copper plus into the solution. In this case, we're adding that into a 1 liter solution, so we can directly say that the concentration of copper plus is going to be the same amount that we are given in mole, because we have 1 liter of solution. And we're assuming that the addition does not change the volume. So the first thing that we need to do is doing our ice table. But we know that the formation constant for this case is up to 10 to the 24. So that means that essentially all of the copper plus it's going to react to copper CN2 minus, right? So we need to find the value for x. One thing that I want you to know is that there are two different ways to do it, but the kind of annoying thing in this case is that using the traditional method that we employ in most of the cases in acid and bases in order to find the portion that is dissociated, it is not going to work so well because the value for Kf that we have is very, very large. So there's no way for us to know directly the result. So we're going to do the following procedure. We have these concentrations of cyanide minus and of copper plus in our solution. The amount of change that is going to react, it is going to be essentially and value of x. In this case, we would have minus 2x and we would generate x over here. So that means that at equilibrium, we would get 1.01 times 10 to the minus 2 minus x, 1.31 minus 2x, and x over here. So now, we could go ahead and write this down into our formation constant and try to solve the equation, but you're going to find that that is quite hard to solve in the sense that you're essentially going to find that x is going to be 1.01 times 10 to the minus 2. So the first step is that we're going to assume that x is essentially the initial value for the concentration of copper 2 plus. So my initial concentration is going to be 1.01 times 10 to the minus 2. In this case, the result is going to be 1.2898. And over here, I'm going to have 0. So why am I doing this? Because I can later go ahead and look at the inverse reaction. This coordination complex can go ahead and produce copper plus 2 equivalents of cyanide minus. And what would be the formation constant? The formation constant, it is going to be in this case, the equilibrium constant, let's write it down as Kc, would be the inverse of the other one, so 10 to the minus 24. The reason why the first one doesn't give you accurate results is because the 10 to the 24 is going to make your calculator give you a result that is way below precision. So essentially, for all solutions, you're going to find that x is going to be equal to 1.1 times 10 to the minus 2, which is going to be nonsense, right? Well, not nonsense, but it's a bad approximation because of the resolution of the calculator, and even in Wolfram Alpha, you get similar results. So what we're going to do is we're going to get another ice table, but now things are going to change a little bit. We're going to start with 0 and over here with the new concentration that we found, 2898. The amount of change that we're going to get, we're going to call it x minus x plus 2x. And finally, at equilibrium, we would get 1.01 times 10 to the minus 2 minus x. We know that this x is going to be a small x, and 1.2898 plus 2x. So with this, our value for Kc for this system, it is going to be concentration of copper plus, concentration of cyanide minus squared, divided by my initial value, 1.01 times 10 to the minus 2 minus x. Oh, sorry, concentration of the complex, right? I went a little bit ahead of myself. So concentration of copper, Cn2 minus. Perfect. So now we can replace the values. This becomes x times 1.2898 plus 2x squared divided by 1.01 times 10 to the minus 2 minus x. So we have two different options. One of them would be to find the complete solution for this problem, meaning solving this quadratic expression. And the other one is going to make a simple approximation. We know that x is going to be very, very small, right? So if x is much smaller than 1.01 times 10 to the minus 2, yep, we can rewrite this as 1.01 times 10 to the minus 2 minus x is going to be approximately the same value. And on the upper side, 1.2898 plus 2x is going to be approximately 1.2898, which simplifies our equations. Now, the new equation reads 10 to the minus 24 is going to be equal to x times 1.2898 squared divided by 1.01 times 10 to the minus 2. With this, we get the value of x equal to 6.07 times 10 to the minus 27 molar. And guess what? That x value is the same as the concentration of copper plus at equilibrium. So this would be our final answer. If you plug in this full equation into any software that solves for x, you're going to find that the result is going to be exactly the same, and also our approximation is valid because indeed x is much, much smaller than 1.1 times 10 to the minus 2. And that would be all. Thank you very much.